we were discussing about half power beamwidth, and we were discussing that if we are plotting the radiation pattern, radiation power pattern rather, so we are plotting E square, not E. So what will be this value? When we are plotting E, we took it at 0.707, right? So what will be this value? Obviously, it will be 0.5 now because we are considering the half power, right? So here we will take it from 0.5, not 0.707, as we did for the electric field. Okay? Are you familiar with dB scale? Are you familiar with dB scale? Do you know dB? Yes, yes, decibel, right? It is 20 log 10 V2 by V1, or in terms of power 10 log 10 V2 by V1. No, okay. So dB is usually it is used to the engineering way of giving the measuring ratios, and we usually measure the ratios of voltages or powers. For voltages, we take 20 log V2 by V1, okay, and for its power is proportional to the square of the voltage, right? So in terms of power, we take 10 log P2 by P1. So if P2 is equal to 0.5 of P1, what will that be in terms of dB? Suppose P2 is 0.5 times P1. So what will be the ratio in terms of dB? Yes, yes, exactly. Exactly, both. Yes, exactly. So what will be this in terms of dB if P2 is 0.5 of P1? This will be 10 log 0.5 P1 by P1. So P1 gets cancelled. That is 10 log 0. Exactly. Minus 3.01 is the exact answer, but we often approximate minus 3.01 as minus 3 dB. Okay. Minus 3.01 is the right answer, but as often we approximate it as minus 3, right? So minus 3 dB means half power. So can you tell me if what P2 is 0.25 of P1, then what will be in dB without using logarithms? Without using calculators or logarithms, tell me if P2 is equal to 0.25 of P1, what this will be in dB? No calculator or no log tables allowed. Yes. How did you calculate? Or minus 6 dB approximately. Right. So see the advantage. If the square is becoming twice, right? What is the advantage in terms of dB? That in log scale, multiplication becomes addition and powers become multiplication. Cube becomes multiplication of 3, raised to the power 4 becomes multiplication of 4, like that. And if it is in multiplication P1 and P2, then in dB scale it becomes log P1 in dB plus P2 in dB. Okay, so this is the advantage. Just one more point before we stop dB here. Do you know what is dBm? Do you know what is dBm? Unlike dB, which measures the ratio, dBm, it measures the absolute value. Okay, and we usually measure the absolute value of power. Or how to measure dBm? Suppose we have power equal to P watts. Suppose I have power P watts. So in dBm, it will be 10 log 10 P by 1 milliwatt. Okay. So what is 1 watt in dBm? What is 1 watt in dBm? Often the received power is measured in dBm. Very often, not in watts. What is 1 watt in dBm and why, we will see. We will see when you see the sanitary cooling structures. It becomes very easy when you say it in dBm instead of watts. So what is 1 watt in dBm? Can anyone tell me? Divided by P. Yes, and what is that, Niloy? What is log 10? What is log 10? 1. So it is 30 dBm. And what is 1 microwatt? What is 1 microwatt? Very good. I understand. Is it okay? Did you understand? You understand? Any doubt regarding dB and dBm? Anybody? Is it clear? Okay. So now tell me, if we plot this pattern in terms of dB, how to find the half power bandwidth? If we plot this pattern in terms of dB, how to find the half power bandwidth? It's beamwidth, not bandwidth. Okay, then I make some questions. Beamwidth. And bandwidth of antenna is also very important to see it, but here we are focusing on beamwidth. So how to find the half power beamwidth in terms of when we plot E in dB scale? In lab, we usually plot it in dB scale. Unfortunately, you cannot have that lab because the university is closed. You have to do some other labs. So if we took dB scale, what will be here? What should come here? The red circle area. Very good, -3. Is anybody okay with it? Everybody okay? This will be indeed be -3. Very, very good. Okay, why -3 dB is clear to all? Simply use this formula, 10 log 10.5 to the -3. Right? So we can plot our radiation pattern in terms of absolute voltage or absolute value of electrical magnetic field, or in terms of power in linear scale in watts, or in terms of, okay. The dB one is the most. So far okay with everyone? No question, any questions so far with antennas? Am I missing something? So far any questions from anybody? Great. To the next topic. isotropic directional and omnidirectional. What is an isotropic antenna? An isotropic antenna is an antenna which radiates equally well in all directions. You understand? It radiates equally well in every possible direction. Right? Is it okay? So what will be the radiation pattern of isotropic antenna in E plane look like? What will be the radiation pattern of an isotropic antenna in E plane look like? Anyone? Very good, circular. And in H plane? And in H plane, how will it look like? Again circular, absolutely. Is it okay? No matter which plane we choose, the radiation pattern of an isotropic antenna is always circular. Is it okay with all? The radiation pattern of an isotropic antenna is always circular no matter whichever plane we are choosing. Right? Because it radiates equally well in every possible direction. What is a directional antenna? Any antenna which is not isotropic is a directional. Is it okay? Any antenna which is not isotropic is a directional. So then what is the third one? Omnidirectional. Which antenna? Okay, isotropic antennas do not exist in real life. Just like frictionless surface and many other things, or weightless strings, isotropic antennas are also conceptual. It does not exist in real life. Okay, every antenna which exists in real life is directional. Okay, every directional antenna, any antenna which is not isotropic is directional. Let me write it. Is it okay? Isotropy and directional is fine. So, what is this? What could be this? Any guesses? What could be omnidirectional antennas? Omnidirectional antennas is a omnidirectional antennas are all directional. Okay. However, then that is isotropic. Then what is the difference between isotropic antenna and omnidirectional antenna? Isotropic antennas have circular patterns in every plane. We have seen that. Omnidirectional antennas have circular pattern in only one plane. In another plane, it is not circular. You understand? Isotropic antennas, they have circular pattern in any plane we can think of. In omnidirectional antennas have circular pattern in one plane but non-circular pattern in other plane. So there are special kind of directional antennas, and omnidirectional antennas do exist in real life. One big example is a dipole antenna. For a dipole antenna, E-plane, this is the E-plane pattern, a figure of 8. This is the E-plane pattern. The H-plane pattern is so this is an example of an omnidirectional. So this exists, this exists, this does not exist. This is a hypothetical concept. Is it okay? Okay? Right. Next. Near field and far field. Okay. In this course, we will focus almost exclusively on far field. Near field, we will see how it looks, but our work will be on far field. Usually, we real life also usually work with far field. What is near field and what is far field? If this is my antenna, the volume closest to the antenna is called the reactive. Then the area around this is called the radiating near field. And everything else in the universe is called the radiating far field. Okay. So the areas which is very close to the antennas, where the reactive components they dominate, that is the reactive near field. This area is this radius is R1, that is equal to 0.62 d cube by lambda. D is maximum dimension of the antenna, and lambda is obviously radius. And this radius is the famous R2 equal to 2d square by lambda. The radiation pattern of the antennas in the near field and the far field will be completely different. And when we are saying radiation pattern, we are saying the radiation pattern in the far field. So what are the differences between them? In the near field, there could be the reactive fields which are dominating. What are the reactive fields? Reactive fields is that which will be positive in one cycle and negative in the other cycle, which actually do not consume any power. You remember Poynting vector? We discussed Poynting vector. So we had something like, what was in the LHS of the Poynting vector? That right. Then there was a WE minus WM dV plus half those EEC by don't need clear. Okay. So in the near field, these terms dominates. Okay. As we go further from the antenna, the reactive terms diminish and the radiating terms they don't. Okay. And what is the far field? In the far field, we have the very famous and very convenient equation that H equal to E by theta. This is valid only in the far field. You cannot use this in the near fields, right? We will focus exclusively on the far field. Any doubts? In the near field region, the reactive elements dominate. In the far field, the radiating elements. When we discuss, when we derive the expressions of the E and H field antennas, we will find that some terms they have 1 by r square dependence, some terms they might have 1 by r cube dependence. Obviously, when r is large, the terms with r square and r cube they rapidly fall to 0. Okay, and this 1 by r square. Okay, sure. What happens in near field? In near field, the reactive components they dominate. And usually, when we derive the expressions, the reactive components they have 1 by r square or 1 by r cube dependence. So, if we increase r or if we move further away from the antenna, the obviously 1 by r square or 1 by r cube will fall much faster compared to 1 by r. Okay. So, these terms fall very rapidly to 0, right? And when we are far from the antenna, we have E equal to E naught by R. It is for falling linearly, and H is H E by. Is it okay? And the rough boundaries they are like this. It is not like that once you cross here, the reactive components all of a sudden become 0. Not like that. They fall outside this area. We do not consider them. We assume that they are insignificant as compared to the radiating. Is it okay? Is it okay? Any other questions? We will consider only the far field. This is also called the Fresnel zone. Sorry, the Fraunhofer zone. Not Fresnel. It's also called the Fraunhofer region. And this region is also sometimes called the Fresnel region. This is silent. Is it okay? Okay then. Let us ask you some questions of maths. What is 1 radian? We often use this. What is 1 radian? Anybody? What is 1 radian? We use radians. Okay, pi by 180 degree. Yes, true. But what do we mean by 1 radian? Can anyone define a radian? Suppose I am drawing a circle. Okay, so a bad circle. Okay, this radius is 1 unit. So what will be 1 radian in this circle? If we draw an arc, okay, if we draw an arc theta AB, then what is the length of the arc AB? What is the length of the arc AB? We know that length of the arc is equal to arc times theta. Now can you define radian from this? Can you define radian from this? Using this, can you try to length of an arc with a unit radius circle? Close, but not quite there. If this length is, if this length of the arc, why theta? If this length of the arc AB is equal to the radius of the circle, then this angle subtended is 1 radian. For theta, 1 degree, don't big degree in that. And length of the arc is this. Instead, if I say it like this, do you agree? The length is equal to the radius, obviously the angle has to be 1 radian. Okay, so this is 1 radian. Now, do you know solid angle? Do you know solid angle? Steradian. What is that? This is required for antenna. Sorry. Yes, exactly. Right, right. What is that? From the similar to the radian definition. Can anyone guess what is that? So obviously we'll consider a cube now, no longer as circle. What is 1 steradian? Anyone try to find out what could be 1 steradian? Suppose I have got a sphere. Okay. It's even worse. Okay, this is center, right? So I take a circle on the surface and the angle subtended, if I say, is omega. So when omega is 1 steradian, then if this is area is, this angle is d omega, this area also is dA, then we define d omega is equal to dA by r square. So when omega is 1 steradian, R is always the radius of the circle. So sphere. R is the radius. So when omega is 1 steradian, if the area of the sphere is equal to the square of the radius of the sphere. But Ritika, the area of a sphere is equal to 4 pi r square. It can never be equal to r square. Think that very well close, but think a little bit more. Equal to the, yes, very good, very good, very close and very good. So what she is saying is that if this area is equal to r square, then this angle is equal to 1 steradian, right? Which is correct. Or in other words, if I say if this area is equal to the area of a square with side r, then this angle is 1 steradian. Exactly what you have said. If this area is equal to the area of a square with side r, there also it is, the area would be r square. So this will be 1 steradian. Is it okay? Is it clear? Any doubt, any questions? To solve a problem. I am using this book, Balanis. Okay. Suppose what? The last problem only. Yes, okay. Then you can go to the control step. We'll continue this from Monday. Sorry. Can you try this problem? Hello. Sorry. Okay. So how to solve this problem? Theta was dA by r square. So what is dA? dA was r sine theta d theta d phi. Theta varies from 0 to pi by 6. Phi varies from 0 to 2 pi. So r square. So this will be dA by r square. R square is comes out of the integral 0 to 2 pi d phi 0 to pi by 6 sine theta d theta. So if we solve this integral, we will get the answer of 0.8356. Okay. Okay, somebody has tried. 2 pi times 1 minus. Can you just check? Arpit. Yes, sine to there will be cos pi by 6. Yes. Arpit, you could be right. Niloy's answer is 2 pi times 0.13. Check whether it's that or not. Yes. Close. Okay, very good. Very good. So any doubts, any problem, doubts regarding this question? Anything else to discuss? Okay then.